I want you to imagine two balloons that have each been charged by the method of conduction. Perhaps each balloon was rubbed with rabbit's fur or something like this. And they've both been charged to the exact same amount. We'll say each balloon carries a charge of positive 1.4 microcoulombs. So when allowed to suspend from the ceiling, the mutual repulsion between the two balloons causes them to hang at an angle other than vertical, right? They repel one another. There's a force that Q2 exerts on Q1, pushing it to the left, and there's an equal amount of force by Newton's third law that Q1 exerts onto Q2. And so the combination of forces produces this angle of 60 degrees between the two strings. So we can figure out what's the amount of mass of the two balloons, assuming they're the same in this problem, if we apply Coulomb's law. So we'll make a free body diagram, and there's a couple forces you're already familiar with. You know there's going to be some tension in the string, so I'm making a free body diagram for the orange balloon. Call that T for tension, and obviously a pull of gravity acting straight down. And if those were the only two forces, this would not represent equilibrium, right? There's got to be another force that keeps it in equilibrium. In fact, we can put in an x and y axis so we recognize there's a component to the tension vector along the x-axis, and there's a component to the tension vector along the y-axis. And your intuition is right. This component of tension that lies along the y-axis is going to be balanced out by gravity. So there must be another force pulling to the left or pushing to the left, and that's the force of electrostatics that keeps this whole system in equilibrium. So we'll call that F subscript E for electrostatic force. Okay, so the angle, we can bisect the 60 degrees and say that each string makes an angle of 30 degrees from vertical. So if we incorporate that into our free body diagram, there's an angle of 30 degrees. So let's clean up the free body diagram, make it a resolved free body diagram. There's a component of tension Ty that's equal to T cosine theta. There's a component to the right, Tx equal to T sine theta. There's an electrostatic force of repulsion to the left, and there's a force of gravity, mg, pointing down. So we're going to say that T sine theta is equal to the electrostatic force, and we say that T cosine theta is equal to mg. But this is the question: how do we calculate electrostatic force between two charged particles? Well, as long as we know the distance between the two, and we do, it's 80 centimeters in this case, we'll call that, we'll give a variable for that, or a symbol for that distance, we'll call it r. The electrostatic force is governed by Coulomb's law, and Coulomb's law is very similar to Newton's law of universal gravitation. So you recall, if you have something like, move this diagram out of the way, excuse me. If you have something like a planet and a satellite that orbits around it, say the planet has mass capital M, the satellite has mass lowercase m, and from center to center, the distance between them is r. Then we know the force of gravity between the two is a universal constant times the mass of the attractor times the mass of the orbiter divided by the distance between them squared. Well, in the case of two charged particles, Coulomb's law says the electrostatic force is equal to a constant multiplied by the charge of one object times the charge of the other divided by the distance between the two of them squared. Okay, so this constant is about 9 times 10 to the 9th Newton meter squared per Coulomb squared. If you like more sig figs, we'll say it's 8.99 times 10 to the 9th. And if you are really interested, this K is actually a a combination of more fundamental units, k is equal to 1 over 4 pi epsilon naught. We won't talk about this quantity epsilon naught for a couple of chapters, so you'll see this again at some point. For now, we'll just give a value to the constant k. Okay, so t sine theta then is equal to k q1 q2 over r squared. However, in this example problem, we've chosen to let q1 and q2 be equal to one another, so we could change this to k q squared, right? q1 times q2 is just q times q squared, divided by r squared. So to make tension disappear from our equation, we can just divide one equation by the other, and tension will cancel out. Sine over cosine gives us tangent theta, and k q squared over r squared divided by mg can be combined to k q squared over mg r squared. So in this problem, we were trying to figure out what is the mass of either balloon. So we just need to do the algebra to isolate for m. So if we do some cross multiplying, we find that m is equal to kq squared over r squared g tangent theta. Okay, grab your calculators. We'll write out the numerical values. K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. The charge in this problem was given as 1.4 microcoulombs. We call that 1.4 times 10 to the negative 6 coulombs. And don't forget that quantity is squared, divided by 0.8 meters. That quantity is also squared. 9.8 Newton per kilogram is the gravitational field strength, assuming this demonstration is near the surface of the Earth. I think that's a fair assumption. And lastly, tangent of 30 degrees. Let's look at the units before we do the number crunching. These coulombs get squared, so they cancel with those coulombs squared. These meters get squared, so they cancel here. Newtons cancel newtons. Okay, so we're left with the inverse of kilograms in the denominator, so this is good. Our overall answer we know is going to be in kilograms, as it should be since we're solving for mass. So let's see what we get. Bear with me. Okay, so the final answer comes out to be 0.00487 kilogram, which is very nearly equal to 5 grams. Great. Here's another example of Coulomb's law. Coulomb's law is bound by the superposition principle. Meaning, all that Coulomb's law really gives us is a way to find the electrostatic force between any two charged particles, 1, 2. But we could have a system where there are 1, 2, 3, 4 charged particles. For example, the charge at the origin could be 5 microcoulombs. The purple charge we've labeled as number 3 here could be 4 microcoulombs. Charge number 2 could be negative. It could be negative 3 microcoulombs. And then charge 4, we'll say, is positive 6 microcoulombs. Now let's give some distances. Say the distance between these is 4 centimeters. There's 3 centimeters. Oh, okay, so those are convenient values. I think all of you realize then, right off the top of your head, that the distance here would be 5 centimeters. This is a 3, 4, 5 right triangle hidden in this diagram. So the question is, if we could somehow fix all these charges in place. I don't know how we do that. There's some sort of form of super glue that we can use to tack them down. Whatever the case is, these are not charges that are free to move around. They're fixed in their locations. And for the sake of this question, we'll say we're trying to figure out what's the net amount of force acting on the 6 microcoulomb charge. So the only way to solve this is to apply Coulomb's law 3 times. We'll find the force between charge 1 and charge number 4. Since both these charges are positive, if you allow me, I'll make a free body diagram for the 6 microcoulomb charge. So I'm going to put a dot right here. I'm going to say there's got to be some force pushing this way, which represents the force between charge number 1 and charge number 4. So I'll just use this notation. We'll call this F14. And we'll use Coulomb's law to figure out the magnitude of that force. Okay, then we also need to pair up charge number 3 with charge number 4. Again, these are both positive charges, so we know that's going to be some amount of force pushing to the right. We'll call that F34. And then the last pair of charges we have to pair up is charge number 2 and charge number 4. Now, one is negative, the other is positive, so that's going to be a force of attraction. We'll call this F24. Now, certainly we could also pair up and figure what's the force of interaction between charge number 1 and charge number 2, but that in no way factors into the net force on charge number 4, okay? So let's see. Let's just find each one of these individually and work it out. So F14. Oh, and by the way, before we get there, I think you know that the angles in a 3, 4, 5 right triangle are 37 degrees, 90 degrees, and 53 degrees. So we already know this value in our free body diagram, 37 degrees, okay? So the electrostatic force between charge 1 and charge 4 is K Q1 Q4 over R14 squared. This is going to be 9 times 10 to the 9th. I'll leave out the units this time since we saw before that dimensionally everything seems to work out as long as we assume that K is in units of Newton meter squared per Coulomb squared, and our charge is in coulombs and our distance is in meters. Everything's going to work out. So I encourage you in your own work to include the units, but for the sake of time, I'll leave them out in this lesson. So charge number 1 is 5 times 10 to the negative 6 coulombs, and charge number 4 is 6 times 10 to the negative 6. Oh, I say I'm leaving out units. And that's divided by 0.05 meters quantity squared. All right, now let's find the force between charges 3 and 4. So again, 9 times 10 to the 9th. Charge 3 is 4 microcoulombs, 4 times 10 to the negative 6. Charge number 4 is always going to be 6 times 10 to the negative 6, and the distance between these two is 0.04 meters quantity squared. And then the force between charges 2 and 4, 9 times 10 to the 9th, times 3 times 10 to the negative 6th, times 6 times 10 to the negative 6th, divided by 0.03 squared, right? The distance between these is this same 3 centimeters indicated here. Now, you might have caught a mistake. You might say, wait a minute, this is supposed to be negative 3 times 10 to the negative 6. Well, I say no. Really, we've already accounted for the fact that this is a negative charge by drawing this force vector in the downward direction. Okay, we haven't neglected the negative sign. We treated that by drawing this vector in our diagram in a particular direction. So what we're really interested in now is just a way to find the magnitude of the force. In fact, the way I wrote Coulomb's law to begin with here, I've really only written a form of it that allows you to solve for magnitude. If you want to solve for magnitude and direction, we have to write out Coulomb's law with a little more detail to it. Let's just be general about this one. If this represents some charge Q1 and here's some other charge Q2, then we can put an origin at the center of charge number 1 and make a line through the two of them and call that our radial axis. If I make a vector that's exactly 1 unit long along that axis, that's a vector known as r hat. So truthfully, force is a vector quantity. So if I were to multiply the scalar quantity k times the scalar quantity of charge 1 times the scalar quantity of charge 2 divided by distance squared, which is also a scalar, then this equation doesn't seem to be in agreement. We've got a vector on the left side of the equation and all scalars on the right side of the equation. But if I multiply this times r hat, I haven't changed the value of my result because r hat has magnitude of 1. Okay, so that's the full form of Coulomb's law, but often we're really not so interested in the direction. We can take care of that just by graphically drawing forces in a free body diagram. So if I just want the magnitude of this, then I don't have to concern myself by multiplying it with the vector r hat. Okay, in any case, grab a calculator and let's see what we get for each of these quantities. Again, bear with me as I compute. Okay, so this comes out to 108 newtons. This comes out to 86.4 newtons. Oh, that's not right. Let me try again. Sorry, this comes out to 135 newtons. And then the last force. (180 newtons). Okay. Well, I can't just take all three of those quantities and add them. This is not scalar math. If we relate this back to our free body diagram, we've got a vector at an angle of 37 degrees whose magnitude is 108 newtons. We've got another vector pointing to the right whose magnitude is 135 newtons, and then another vector pointing straight down with a magnitude of 180 newtons. So really the only force we need to break into components is the one with a magnitude of 108 newtons. So let's turn this into a resolved free body diagram. Okay, so the 135 doesn't change. The 180 isn't changed. And all I need to do is 108 times the cosine of 37 degrees. But cosine of 37 is the same thing as 4/5, just like the sine of 87 is the same thing as 3/5. Okay, so 4/5 of 108 gives us 86.4 newtons, and 3/5 times 108 gives us 64.8 newtons. So we know that the downward force is greater in magnitude than this upward component. So the end result, we have some downward force component, a large amount of force component to the right. If I add 135 with 86.4, we get 221.4. If I subtract 64.8 from 180, we get 115.2. So the net force we can find using the parallelogram method of vector addition, and really then that comes down to applying the Pythagorean theorem our net force is equal to the square root of 221.4 squared plus 115.2 squared. And we find a net force of 250 newtons. Okay, so that's what I mean when I say we can apply the superposition principle when using Coulomb's law. At best, we can only pair up any two charges with each other. So sometimes we have to use Coulomb's law multiple times in order to find the net result for the force on any given object. Hey, thanks for watching.